So for today, we are going to have one more example on how to analyze a CMOS amplifier. So I'm Sir Febus. So we can start. Are you all okay? Can we start?
Yes po, sir.
All right. So again, when doing the amplifier analysis, it will always be two parts. So part one will be large signal analysis or DC analysis. And part two will be the AC analysis or the small signal analysis. All right. Then the last part, we can add part three, that would be to combine the results of DC and AC analysis. All right. So here is an example of a common source amplifier. Okay, can you confirm if you can see yung cursor ng laptop ko?
Yes po, sir.
All right, so we have here a common source amplifier. Since the input voltage is connected at the gate terminal of transistor M1 and the output wherein the load resistor is connected is attached at the drain terminal of M1. So this makes the circuit a common source amplifier. Input at gate and output at the drain terminal. And as for the source, it can be either bypassed to the ground or unbypassed. So pwede pa rin yun, no? This will still be a common source amplifier. So effectively, the source terminal will be common to the input gate and to the output drain terminal. Okay? So we have a voltage divider bias provided by resistors R1 and R2. And we have the DC supply, VDD, equal to 12 volts. Then you have the drain resistor of 1 kilo ohms. Then source resistor of 1 kilo ohms. Then you have the input coupling capacitor CC1 of 10 microfarad. Output coupling capacitor CC2, 10 microfarad. And a bypass capacitor CB1, 100 microfarad. Then the load RL has 1 kilo ohms. Then the input voltage, it says here that it has an AC amplitude of 10 millivolts. All right. And then for our M1, M1 is an NMOS with this following parameters. So the threshold voltage when the source to bulk voltage is 0, or that is the VTO. VTO is equal to 0.7 volt. Transconductance parameter Kp is 750 microampere per volt squared. Lambda is 0.1 per volt. Then gamma is 0.2 raised to 0.5, no? Square root yung unit neta. Then P, or the surface potential, equal to 0.7 volt. Then we also indicated the internal capacitance of our MOSFET. So we have the gate drain overlap capacitance of 5 picofarad and the gate source overlap capacitance of 5 picofarad. Okay? And we are going to do a operating point analysis. So naglagay tayo ng .op. Okay, clear?
Yes po, sir.
Okay, thank you. So I hope you are all familiar, no? So I'm using the LT Spice. So when doing the DC analysis, we are going to short out the AC input voltage, all right? And we are going to use only the DC supply. And at the same time, we are going to consider all external components as open circuits. So coupling capacitor 1 will be treated as open circuit. So the input voltage, although it is already shorted, is no longer connected to the gate. Coupling capacitor CC2 is open circuit. Therefore, RL will no longer be connected to the drain. And then the bypass capacitor, CB1, is open circuit. Therefore, RS will be connected to the source and ground. So applying these assumptions or conditions, this will now be the DC or large signal equivalent circuit. So what will remain is the biasing circuit. So we have here again the voltage divider bias of transistor M1. Then for our analysis, we have to check the VSB. Check the schematic diagram if the bulk is not connected to the source terminal. So if bulk is shorted or connected to the source, that means the voltage between the bulk and source equals 0. Therefore, if BSB is 0, VTH will be equal to parameter VTO. But in case the bulk is connected somewhere else, you have to determine first the source and bulk voltage. So mag-analyze ka and then determine the value of the VSB and then plug it in this equation. So VTO, gamma, and P are all provided transistor parameters. So after knowing the VSB, we should be able to determine the threshold voltage. So normally, this is our first equation for the DC analysis. Okay, is that clear?
Yes po, sir.
All right. So in case hindi pinakita kung nasaan, halimbawa sa schematic diagram, bulk is not shown, we are going to assume that it is shorted with the source. Yun yung default natin. No? Default is BSB is equal to 0. Therefore, BTH is equal to VTO. Yun yung default. But in case it is obviously depicted in our schematic, so we have to solve first for the BSB and determine the VTH. The next, we are now going to indicate the VGS. So this is the input voltage, and the VGS must be greater than the VTH for M1 to turn on. Okay, so we will compare VGS with the VTH. If it is greater than the VTH, then we can say M1 is turned on and we will have the drain current. Okay, then aside from the VGS, drain current is also affected by the VDS. Okay, and we are going to use the MOS device model or equation for the drain current in the saturation condition. So our equation is drain current is equal to 1/2 Kp W over L times VGS minus VTH squared, all multiplied by 1 plus lambda VDS. So based on this model, we can see that drain current is affected by the input VGS. It is also affected by the VDS, and it is also affected by the VTH, which is affected by the VSB. So lumalabas, drain current has 3 input voltages, no? Although VGS yung merong dominant effect. So aside from the dominant VGS, drain current is also affected by VDS due to the channel length modulation and by the BSB due to the body effect. Okay, is that clear yung principle na yon?
Yes po, sir.
Thank you. So for our DC analysis, continuing with IG equal to 0, then the current flowing through R1 will be the same current flowing through I2. All right, then we can have the voltage loop at the input and have this equation. So you have the VDD and then minus IX multiplied by R1 plus R2. So that will be our input equation. Then we can also indicate the input gate voltage, that is the voltage across R2. So we can write gate voltage equal to Ix times R2. So normally circuit parameters are provided. So we know VDD, R1 and R2, so we can solve for Ix. Then after knowing Ix, we can solve for the gate voltage. Then afterwards, or another way, there is another way of solving gate voltage. We can apply voltage division. So get the total voltage multiplied by resistance R2 divided by the total of R1 and R2. So we can also use this to determine the gate voltage. Then, after knowing the gate voltage, we can now determine the VGS. So for the VGS, we have to indicate the voltage drop across RS. So the current flowing in this part of the circuit is source current, which is the same as the drain current. So we can have a voltage loop, and that would be gate voltage as equal to VGS plus drain current times RS. So we already determined VG at this point. So VGS and ID will be the unknown parameters. So meron kang dalawang unknowns dito, no? Then another equation, on the output side, we indicate the drain current along RD. Then you have drain current as well along RS. Then between drain and source, the voltage is denoted as VDS. Then we do the voltage loop along the output circuit. So we'll have VDD minus IDRD minus VDS and then minus ID. So the unknown parameters usually, again, would be the drain current and the drain source voltage. So from our DC analysis, we have this drain current equation as our equation 1. Unknown parameters would be ID, VGS, and VDS. And then for the input circuit, we have this as our equation 2. Unknown parameters would be VGS and ID. And the output circuit will have this as equation 3. The unknown parameters would be drain current, drain source voltage, and drain current. Okay, nasundan ba? Please confirm.
Nasundan pa naman po, sir.
Alright, sige, thank you. So from the equation 2, ito, i-practice nyo na lang to, no? Pero this is how I did the analysis. So from equation 2, I combined equation 3. So substituting the value of VDS in equation 3 to equation 2. And then included as well equation 1 to equation 2. So meron na tayong equation 1 and equation 3 into equation 2. Alright? So yan yung naging equation natin, no? So from equation 1, I substituted the equation for the drain current. So from here, the only unknown parameter would be the VGS. Then simplify this, use the algebra. Ayan, and then I arrive at this equation. Medyo mahaba tingnan, no? So we have this. So what I did is, based on this equation, you have the cube root of BGS, square cube of BGS, square of BGS, then we have BGS, and then we have the constant. So M coefficient is equal to this, N is equal to this, and then P coefficient is equal to this. Then I apply the cubic formula. So based on this equation, A BGS cubed plus B BGS squared plus C BGS plus D is equal to 0. Using the cubic formula, this is how we can solve the parameters A, B, C, and D. All right? Then, use the cubic formula, check it on the internet. I was able to solve for the BGS as equal to 1.39 volts. So if we are going to use cubic formula, we should get 3 possible answers. So select the value of VGS that is greater than the threshold voltage. Yun yung criteria natin, no? The VGS must be larger than the threshold voltage. Okay? Then after solving the VGS, we can now solve the drain current and the VDS. So in this example, for the given circuit, VGS is 1.39 volts and the drain current is 4.61 milliamperes. Nasundan ba? Please confirm. So medyo mahirap sundan, no? Pero yung procedure is from the three equations, from these three equations, use your algebra, or if you are if you have other ways, no, you can use your calculator to solve for the unknowns. So in my case, I use the simplify, combine the equations until I form a cubic formula or cubic equation. Then applying the cubic formula, I was able to determine the VGS. Okay? Or another way, after knowing A, B, C, and D coefficients, you can just go to a website. No? Meron yung MathPapa. I just code in the equation and it will calculate the X, which is equal to our VGS. Alright? Isa rin to. No? So I use the Excel, yung manual calculation, and then I also use this. So perhaps you can also include this in your calculator, no, para ma-solve. Nasundan ba?
Yes po, sir.
Nasundan naman po.
Alright. Now, these are the parameters. Take note of the parameters. So VTO is given, KP is provided, lambda, meron tayong value na 0.1, gamma is 0.2, P is 0.7, and then you have the internal capacitances. So based on the hand calculation, it gave us a VGS of 1.39 volts and a drain current of 4.61 milliamperes. All right, so before we continue, we would like to acknowledge the presence of our ECE chair. No? Nandito si Ma'am Flor, Engineer Valiente. So she will be observing our discussion for today. Good morning, Ma'am Flor. Okay, so continuing. Good morning po, ma'am. Very good. Okay, continuing. So based on the hand calculation value, I run our LT Spice for the .op or the operating point simulation. And what I got is a VGS from the operating gate voltage minus the operating source voltage. So I got a VGS equal to, ilan to bale? VGS equal to 2.96 volts. So 6 volts minus 3.04. Dito sa taas, VGS is also indicated as 2.96 volts. And the operating drain current is equal to 3.04 milliamperes. So if we compare that with our hand calculation, we can notice a mismatch between the hand calculation results and the LT Spice simulation results. All right, so further review of the simulation gave us the root cause of this mismatch. So we have to, in our hand calculation, we indicated the width over length ratio. So in order to include that in the simulation, instead of using the NMOS component in the LT Spice, we can use the NMOS 4. So this is the 4-terminal NMOS, wherein we can specify the length and the width, the same as with our hand calculation given. So I It included the 100 micrometer for the transistor width and a 5 micrometer for the transistor length. Similar with our hand calculation. And by doing that, we were able to match the hand calculation results with our operating point simulation results. So we had BGS equal to 1.39 volts and a drain current of 4.61 milliamperes. All right, nasundan nyo ba? Please confirm. Nasundan ba? Please confirm.
Sir, pwede pong paulit lang po dun po sa part para maayos po yung mismatch po dun sa hand calculation at sa
Alright.
LT spice po.
Okay. So regarding dun sa mismatch, let me hide yung controls. Okay, going back. Medyo malayo ang balik, no? Alright, dito siguro. So from the transistor model, we have Kp, we're given with the parameters, no? Meron tayong Kp, lambda, then the W over L, meron ding value to, no? Hindi ko lang naipakita sa given, but I used a certain value for the width and length in my hand calculation. So that's why we're able to compute for certain value of BGS as equal to 1.39 volts. So naka-define yung width and length of the transistor. Okay? Now, when using the NMOS component, the width and length are not clearly defined, or by default, the ratio is equal to 1. So yung width over length nito, default nito is equal to 1. So if I'm using 100 over 5, I'm actually using a ratio of 20. All right? So that is the cause of the mismatch. In the hand calculation, I'm using W over L equal to 20, while in the simulation, the LT spice is using the default ratio equal to 1. So that's why we have the mismatch. Now, it's either you correct the hand calculation, set the W over L equal to 1, or you can adjust the LT spice. So what I did, I adjusted the LT spice settings by changing the M1, the transistor M1. Instead of using the NMOS component, we can select the NMOS 4. Ito yung pwede nating gamitin, no? So, for example, can you see my LT spice?
Yes po, sir.
All right. So in the components, you have the NMOS, and then we have here the NMOS 4. So the NMOS 4 allows the settings of the transistor sizes. You can adjust, you can set the length, you can set the width, and other sizes. All right? So I replace the NMOS with the NMOS 4 component so that I can set the W over L equal or the same with the hand calculation. So 100 micrometer over 5 micrometer will give us a ratio of 20. Okay? And by doing that, we're able to match or have the same results with the our hand calculation and the LT spice simulation. Okay? Nakuha mo yon?
Yes po, sir. Nakuha na
All right. Sige. Thank you. Now, the same circuit, but this time, notice, all right, so andito na yung cursor natin. No? So notice that the lambda, what if lambda is set to 0 or gamma set to 0? So there are sample problems for simple analysis. We can assume that lambda is equal to 0 or gamma equal to 0. So by having this, if let's say assume or set lambda equal to 0, then our DC analysis would be simplified. So this is the drain current model. And if lambda is equal to 0, then this equation will be simplified into this. So the unknown parameters will be reduced to 2. So the unknowns would just be drain current and the VGS. So we do not need to determine the VDS. So this would simplify the solution. Instead of using the cubic formula, we just need to use the quadratic formula. Okay? So drain current would be this one. This will be our equation 1. Then for our input circuit, still would be the same. BG equals BGS plus IDRS. So you have two equations, two unknowns. Use your algebra to arrive at a quadratic equation. So you have BGS squared plus A times BGS plus B equal to 0. Then use the quadratic formula or quadratic equation to solve for the VGS. So again, when using the quadratic, you'll be getting two possible values of BGS. So we are going to select the value of BGS that is greater than the threshold voltage. So yun yung tamang value ng BGS. Okay? So normally you'll be getting negative and positive value. So get the positive, and if both are positive, kung pwede man yun, just select the value of BGS that is larger than the VTH. Again, is that clear? Please confirm.
Yes po, sir.
All right, sige. Thank you. So with this, we do the hand calculation with the assumption that the lambda is equal to 0. So we get a BGS of 1.48 volts and a drain current of 4.52 milliamperes. And for the LT-SPI simulation results, we're also able to determine the same VGS and drain current. Okay. Now, continuing, this time we proceed on the AC analysis. So after knowing the DC operating parameters, so after knowing the input VGS, the VDS, and the operating drain current, we can now proceed on the AC analysis. So in terms of LT-SPI simulation, we are going to change the operating point simulation to AC simulation. So we have here that AC, use the decade. So that means the change in the frequency will be by 10. So times 10. So starting from 1 hertz, ending at 100 kilohertz. So the LT-SPICE tool will increment starting from 1 hertz. The next frequency would be 10 hertz, so times 10. So 1 times 10, 10 hertz. Times 10, 100 hertz. Times 10, 1 kilohertz. Another times 10, 10 kilohertz. And then another times 10 or another decade will give us the 100 kilohertz. And for every decade, the simulation tool will get 10 simulation points. Yun yung nakalagay na 10 dito. Okay? And from the AC simulation result, we are going to measure the magnitude of our gain. In this example, we calculated the gain by getting the maximum value of the output voltage divided by the voltage at the input. Okay? And also notice, we continue with the assumption that lambda is 0 and gamma is 0. Okay? So for our AC analysis, this time we are going to assume that the DC supply is shorted and we are going to apply the AC input voltage. And at the same time, so before that, applying the AC analysis, before we continue with the equivalent circuit, we can solve for the small signal parameters. So we have the transconductance parameter GM equal to the square root of 2 times parameter KP times transistor size times the operating drain current. So from the DC analysis, we're able to determine the drain current So Kp and W over L are given. So we can solve for the small signal transconductance GM. Okay? And we can also determine output resistance, the resistance between the drain and source of the transistor using this equation. 1 over lambda times the operating drain current. So for this AC analysis, we will assume that lambda is equal to 0. So therefore, output resistance, small signal output resistance RO is equal to infinity or equal to the open circuit. All right, so pag dinraw natin, when we draw the AC equivalent circuit, we do not need to include RO in parallel with the current source using the parameter GM. Okay, so first step in doing the AC analysis, determine the small signal parameters, GM and R out if lambda is provided. So based on calculation, the transconductance GM for this given parameters, that is equal to 11.64 millisiemen. So you can recompute on your own and then let us see if we can get the same results para may confidence kayo that you are doing the calculation correctly. So that's why I'm putting the correct answers. So after getting the small signal parameters, we can now proceed in determining the AC equivalent circuit. So at this point, again, we are going to short the DC supply and we are going to use the AC input voltage. So when we consider DC supply as shorted, the nodes of R1 and RD or drain resistor will now be connected to the ground. And another assumption for this is the coupling capacitors will be treated as shorted. So, but for in this example, we first indicated the coupling capacitors, the bypass capacitor, and the output coupling CC2. So we just shorted the DC supply. All right. So from the gate terminal, we can see that R1 is connected between gate and ground. So for the gate, you have R1 connected to ground. As also connected to gate, you have R2 connected to ground. Then connected to gate to the input node, you have the coupling capacitor CC1. And on the input node to ground, you have the Vin. So yun yung input part natin. Then for the transistor, in LT-Spice, I think I used a voltage-dependent current source. So ito yung symbol niya. No? You have the voltage-dependent current source. I already included the transconductance parameter equal to 11.64 millisiemen. Okay? So you have gate, drain, and source. So on the source, we have resistor RS in parallel with the bypass capacitor. Then for the drain terminal, you have RD connected between drain and ground. And between the output node, you have coupling capacitor. Then on the output node, you have RL going to ground. So that comprises the output circuit. Okay, please take a look at the schematic and tell me if you can follow how to produce this equivalent circuit. Please confirm, nasundan nyo ba ito?
Yes po, sir.
Yes, naman po, sir.
Okay, thank you. All right. So here is the closer look of the AC equivalent circuit. Yan, close-up shot natin. No? So for our AC analysis, under the so-called mid-frequency response or the middle frequency response, so this will be our assumptions. We are going to treat the external capacitors as shorted. So CC1 will now be considered as shorted. So the input node will be directly connected to the gate node. Coupling capacitors 2 will also be shorted. So output node or RL will be directly connected to the drain. Then bypass capacitor CB1 is shorted. So this will also short out the source resistor. So that would connect the source terminal of the transistor directly to the ground. So ganyan ang mangyari dyan. Okay? Then for this current source, this drain current is equal to GM VGS. Yun yung value ng current dito. No? Drain current equals transconductance GM multiplied by the input VGS. So the current flowing in this direction would be this magnitude but of opposite direction. So that would be negative GM VGS. Okay, that would be the current flowing through later on through parallel of RD and RL. Now as for the VGS, that is the voltage between the gate and source. Okay, so from the input, you have the input voltage. So since we have a common source amplifier, the input voltage will be applied as gate voltage and will be measured as output drain voltage, and that drain voltage will provide the output voltage. Okay, nasundan ba yung mga notations?
Nasundan po, sir.
All right, sige, thank you. So from here, we can determine the voltage gain. So from the output circuit, it would be ratio of output over the input. So V out over drain voltage multiplied by the voltage gain of the transistor. So output over the input. So times VD over VG multiplied by the input circuit voltage gain. So output is VG divided by input Vin. Okay? And then from the schematic diagram, V out over VD, they are parallel voltages since CC2 is shorted. So they would have the same nodes. So they are equal voltages. So V out over VD is equal to 1. On the input section, since CC1 is also shorted, Vin and VG will have the same nodes. So they are parallel voltages, so they are equal. So the ratio is also equal to 1. Then for the transistor voltage gain, you have drain voltage divided by the gate voltage. Drain voltage is the voltage across the parallel of RD and RL. Drain resistor in parallel with the load resistor. So multiply the parallel resistance with the current flowing from top to bottom to produce the polarity, positive sa taas, negative sa baba. So you have negative GM-VGS, that is the drain current, multiplied by the equivalent resistance. Okay, so that provides the drain voltage. For the gate voltage, we can express that in terms of the VGS. So we can see that VG is actually the same as VGS, since the source is bypassed. So source is directly connected to ground. So the negative of BGS has the same node as the negative of BG. So BG is also BGS. So we can cancel out BGS. That gives us a voltage gain equal to negative GM times the parallel of RD and RL. Nasundan ba ito? Please confirm.
Yes po, sir.
All right. Thank you. Then based on my hand calculation, nakuha na natin kanina yung GM, then we get the parallel resistance. I was able to solve for voltage gain equal to negative 5.82. So we had a magnitude of voltage gain equal to 5.82. So the input voltage will be multiplied or amplified by 5.82 times papunta rito sa output natin. So if we have an input voltage of 10 millivolts, expect that across the output, it will become 58.2 millivolts. Nasundan ba yon?
Yes po, sir.
Okay. So again, I included the correct answer so that when you solve this on your own. You verify whether you are able to arrive at the same answer. Then for the LT SPI simulation, when we run the AC simulation, what is provided is the decibel. So I'm given a gain equal to 15.3053 decibel. Okay, yun yung result nung dot measure natin, no? 15.3053 decibel. So we will convert the decibel voltage gain into the magnitude. So you have voltage gain in decibel is equal to 20 times the logarithm of the voltage gain in magnitude. All right, so 15.3053 divided by 20, then apply anti-logarithm, we're able to arrive at a voltage gain also equal to 5.82 volt per volt. Nasundan ba yon?
Nasundan po, sir.
All right, sige, thank you. Now, notice on the initial settings of our LT SPIs, all right, so dito, tingnan mo. So take note of the AC analysis. So that is that decade, then measure, get 10 points, start from 1 hertz, and then end at 100 kilohertz. So when we analyze this or when we run the simulation, this will provide us this simulation results. So at 1 hertz, you have negative 24 decibels. And then as the frequency increases, then at around 100 hertz, we're able to reach the maximum possible gain of around, ilan yung kanina? 15, no? 15.30 decibels. Yun yung maximum gain natin. Okay? So up to 100 kilohertz, we're able to maintain the maximum gain. So in this simulation result, it guarantees that using this circuit, you can apply an input voltage of with a frequency of around 100 hertz up to 100 kilohertz, and this amplifier circuit will provide the maximum possible gain. Yun yung pinapakita dito sa frequency response natin, no? For a given input frequency, we are showing the voltage gain of the amplifier expressed in the decibel. Then the other graph, kung titignan mo, may dash line dito, no? And it is in degrees. This is actually the phase angle of the input and the output. All right, so starting from around 10 kilohertz to 100 kilohertz, the phase margin is already 180 degrees. So since it is a common source amplifier, we expect that there will be phase reversal or 180 degrees. When the input voltage is positive, expect that across the output, you will get negative voltage. And when the input is negative, expect that the output will be positive naman. So baligtad siya. Positive ang input, negative ang output. Negative ang input, output will be positive. So yun yung ibig sabihin ng 180 degrees natin dito. Nasundan ba? Please confirm.
Yes po, sir.
Alright, so based on the measurement, it provides us a gain of 15.30 decibel and a phase margin of negative 179.985 degrees or very close to 180 degrees. That is from 1 hertz to 100 kilohertz. So again, these are the LT SPI simulation results, and we can convert the decibel into the magnitude. So 15.3 is the same as times 5.82. Okay. Now, I did another simulation, but this time I increased the stop frequency from 100 kilohertz, I made it 10 terahertz. So tinaasan ko na yung frequency, no? Ginawa kong 10 terahertz. So that when we run the simulation, we'll be able to show that at low frequency, you start from low voltage gain, and then up to a certain frequency, you get the maximum gain. And then we did not stop at 100 kilohertz, but continue the analysis up to 10 terahertz. And then at around 100 gigahertz, we can notice that the voltage gain will again start to decrease. All right? So yun yung complete frequency response of the amplifier. Okay? So with this frequency response, we can see that an amplifier will have a maximum voltage gain for within a certain range of frequency. Ito, may kita mo, meron kang maximum gain. When you go lower, when the frequency becomes lower, the voltage gain will decrease or will attenuate. Likewise, when the frequency becomes higher, merong certain cut-off yon, the voltage gain once again will attenuate or will decrease. Naintindihan ba iyon?
Yes po, sir.
All right. And also for a common source amplifier, if you want to operate it at 180 degrees, ito yung recommended frequency range, no? From this point up to this point. All right, so we have maximum gain and then you have 180 degrees operation. So this is the closer look of the frequency response. And again, the voltage gain based on our measurement, that is 15.3 decibels. And then based on the maximum gain, subtract 3 decibels, and that will give us the cut-off frequencies. So that is the definition. When you say cut-off frequency, that is the frequency wherein the gain becomes minus 3 dB or decreased by 3 decibels. So if the maximum gain is 15.3, at the cut-off frequency, the gain is 12.3053 dB. So somewhere here, no? So that in this portion, yung 12.3, that will give us the cut-off frequency. And that would be the lower cut-off. And also, pag tinuloy-tuloy mo yan, you also have here the 12.3 dB. This will give us the higher cut-off frequency. Nasundan ba ito?
Yes po, sir. Nasundan po.
Okay, thank you. So I zoom in ko lang ito para kita natin. So here you have negative 24 to 20. So I just zoom in dito sa area ng ano natin, no? Area of interest. So from 15.5 to 12 dB lang, no? So here we can see the 12.30 dB. So yun yung intersection natin, and then you can estimate the frequency if you are using graphical method, or if not, you can use the dot measure statement, no? Pwede rin yan para you can determine the frequency when gain is equal to 12.3 dB. Okay? So this gives us a lower cut-off frequency of mga ilan yan, parang more than 20 hertz, and a higher cut-off frequency of ilan to? 200, 300, 400, 500, 600. So more than 600 gigahertz. So you can apply an input signal within this range. But I would suggest, yan yung allowed. But I would suggest for optimum operation, I would suggest that we only limit our frequency where the gain is maximum. Okay? Para maganda yung performance. All right, so that ends our analysis of CMOS amplifier circuit.